Okay, so let's start. I am your TA, Suraj Borate, and we are in the week 3 of the NPTL Introduction to Robotics course. I am a PMRF PhD student from IIT Gandhinagar, and today we will be continuing our MATLAB code from the last week, where we left in half, where we just simulated the forward kinematics, and then we also wanted to animate that. Uh, but before that, before we go to that, we will finish the week 3 questions from some old assignment on the NPTL, so that you can, it can help you in solving the questions from the for the current assignment. Um, okay, so there are not, because most of the things we discussed last time and the questions are pretty similar to week 2 questions. I think this time we will be able to finish much earlier. But still, let's revise a bit. So we had seen these rules to. Just let me check. You can hear my voice, right? Hello, hello. Can anyone tell me they can hear
Yes,
my
sir, we
voice?
can hear
Yeah.
your voice.
Okay. Yeah. So we had seen these two. Uh, what we say, images of the book that I recommended, Vidyasagar and Spong. And here there are rules for labeling the axis, right? So first, what we do is we just locate and label all the joint axis with Z0, Z1, and all. And after labeling the joint axis, we establish the base frame around the Z naught, like X naught and Y naught. We just put arbitrarily, and after that, what we do is we locate the origins of each frame by where the common normal to Zi and Zi minus 1 intersects Zi. So what we will look at all the thing again. Uh, and then we establish Xi along the, common normal that intersects uh, Zi minus 1 and Zi. And so Xi is basically perpendicular to both Zi minus 1 and Zi. And then we proceed to put Yi, which is in a way that completes the right-handed frame. Okay, and the end effector frame, we just, copy n minus 1 frame. Uh, okay, and just remember that, the DS parameters, AI, DI, alpha I, and theta I, are basically, so the AI is the distance along Xi, okay, whereas DI is distance along Zi. Zi minus 1. So there are more things to it, but this much if you remember that, okay, AIs are along Xi, so the link lengths are along, usually along Xi's, and DI is the link offsets are along the Zi minus 1. So that can answer half of the questions. And alpha I, the twist angle is, between the Zi minus 1 and Zi, about rotating about Xi. Okay, so alpha is not about the joint axis, it is about the link axis. Or let's say there is nothing called a link axis, but it is along the, x axis. Okay, whereas theta I is the joint variable, and that is along the Zi axis. So if you just remember this, that also can, answer some of the very basic questions, as we will see. And the basic procedure why we are doing all this is, so I had shown you one formula that is a homogeneous transformation matrix last time, and I will pull that up again. So this is, yeah. So this formula is for, every link you will get one matrix like this using the that corresponding links, alpha I, theta I, di, and ai, and you create one matrix for that, and eventually you multiply all this matrices for each link, and you get the total, the ultimate resultant homogeneous matrix that relates the end effector frame to the base frame, like to n to 0, it will relate. So that is the procedure. Today's assignment is much easier than what we did last time. So okay, so let's go back. So let's go to the first this thing, and if you remember what I just told, you'll see how easy it is to answer without even going back and looking at the rules. Okay, so from the below options, choose the fundamental operations involved in making n minus one frame coincident with nth frame. So there is this n minus one frame, and you have to perform some operations like maybe translation and rotation about this four operations we do, right? To four fundamental operations corresponding to each ds parameter is done. And we remember from what I just now said that the theta the theta is the angle where it is rotated about z axis, right? It is not rotated about x axis. So you just see here that okay, that theta n is there. Oh, it's not writing. Okay, so theta n is there, and it is rotated about z axis. So okay, it's fine, it's correct. Theta n rotated about x axis? No. Theta is n is not the rotation about x axis, right? Theta n is about z axis. So that is right. So alpha should be about the x axis. So alpha about x axis. So this is the right option. Okay. Then alpha about z axis is not right. D. So D should be about z axis or x axis. Can anyone tell? So is this option correct?
It is correct, sir.
Can you be loud?
Um, am I audible now?
Yes, yes.
Yes, yes. Yes, I said it's correct, sir.
Okay.
Okay.
So D is about the z axis, and A should be about the x axis, right? So that is how we solve this question, and yeah, so that is the answer. Okay, so let's move on to the next question. And since we have, I think it will be
Sir, could you just
very,
show the answer once again? Sir, could you
yes,
just show the answer once again? Sir, could you just show the answer one more time?
yeah, just see,
Thank you, sir. Please.
or you can see it here also.
Yes, sir. X and
Fine.
yes, sir. Got it.
Okay, so I think the method you just remember. That is more important. So numbers and figures will change in your assignments. Okay, so here they have given us that a homogeneous transformation matrix from wrist and between base and wrist, and they tell us also give us the values of theta 1, theta 2, theta 3, A2, A3, D1, D5, and all. And they ask us the position coordinates of the wrist with respect to the base of the. So you see here it is wrist with respect to base. Okay, so there are no tricks over here. They haven't said anything like base with respect to wrist and all. They have not tried to fool us. So it's fine. Uh, and so they have asked for the position coordinates. So the position coordinates means where? These three values, right? These are the values of the position coordinates. Okay, so if you want to find this, let's we can put the values. So here remember C1 is the short form for cos theta 1, and similarly S1 is for sin theta 1, and C23 is nothing but cos of theta 2 plus theta 3, and similarly. Okay, so 2 3 means theta 2 plus theta 3. Okay, so here there is little bit of a typo, I guess. So I think this is S1 maybe, and okay, so there will be some, there is typo, so there will be slight maybe number error we might get, but you don't worry. Okay, so ignore this term. Okay, this is S23, but they have written it like S2 and 3. It's not like that. Okay, so ignore that. So basically, they have given you the matrix and they have given the values. So what you do, you just plug in the values and check what is the answer. So in order to plug in the values, you can do it by hand, but now I'll just use the MATLAB. So I have so in MATLAB you can see that I have to type this very big matrix, right? Again and again, you have to type cos d of theta 2 plus theta 3. So that will become like very too much effort. So what I did, lazy thing over here. And I made these variables theta 1, theta 2, theta 3 and made the variables S1 cos1, sorry, S1 C1, S2 C2, C2 3, S2 3. Okay, wait. So my MATLAB screen is not recording. Okay, I will have to change over here. Yeah. Okay, so as you can see, I made the shortcuts for S1, C1, S2, C2, S2 3, C2 3. Okay, and gave the values of all these values I could give. So why this D5 is here? Let me check the question. Yes, they have given D5, no problem, but they haven't used it. Okay, funnily. Okay, so that is not a problem. Let's go back to MATLAB. Okay, so this is the code, and we just plug in the values. I think by now you know how to do the matrix, fill in the matrix, and get the matrix. So I just run this. You can do it by hand also. Okay, that is not a problem. Okay, so once I do this, I get the answer over here minus 125 minus 55. Okay, so 0 minus 125 and minus 55. These three entries we wanted, right? Okay, I hope you can see the this thing. It's not too small. We'll try to enlarge it anyways. Okay, so this is this thing, and if I want to take out those values, I will just say A of the fourth column, right? And first three rows. So 1, 2, 3 rows. So colon is like from 1 to third row, and the first argument is about rows. The next argument is about column. So it is first to third row and the fourth column. And if I run this, I will get the 0, 1, minus 125 and minus 55. Okay, this value we might get a small error because it was little bit ambiguous the way they wrote it. So let's just go back to the PPT. Uh, okay. Yeah. So here, if you see, we will get the answer as minus 125.7 and minus 53.5. So this is also the answer. Yeah, this is the answer, and this is what we got in the MATLAB, right? So yeah, I think this is fine. This was too easy. So can we consider the commercial 6-axis articulated arm Intellect 660T as a holonomic manipulator? So in the first TA session, we learned about what is holonomic meaning. So holonomic means that you can move in any direction instant instantaneously. Okay. So the spelling might be little bit this thing, but okay. So this is the idea. Now, if you see this manipulator, so I don't know whether this is actually 660T. I tried to find the image, but it was not there. But I think it is. It should be something like this: 6-axis articulated arm. So this is the first axis. This is the next axis, right? Then this is the third axis. Okay. So using these three axes, the robotic arm can point any position, can reach any position in the workspace. Okay, using this 3 degree of freedom, because these 3 degree of freedom are not parallel, right? So if you imagine the base rotation can rotate the arm like this. Okay, and the second rotation, so it is like a shoulder. So if you see, this is like a shoulder, and you can rotate the arm like this. Then the this particular rotation is perpendicular to it. The second rotation. So this is the first rotation. This is the second rotation. So once you do this, okay, you can sweep 360 degree along this direction, and then you can have some angle around perpendicular to it. Okay, so already you can point along any direction on a sphere using these two degrees of freedom. But then you have additional degrees of third degree of freedom. at this edge, which will allow you to, once you go to one angle and the second angle allows you to reach in that plane. Okay. And the one more degree of freedom in that plane will allow you to, go to any position. So it's kind of, okay, someone joined. I'll add that person. Okay. So it's kind of, so this particular base link will take you to a particular plane. So let's say there are a lot of planes around, like this plane. There are like infinite planes, right? Vertical planes. So this particular base will orient you into one of the vertical planes, and inside that vertical plane, it is like a two-hour manipulator, right? Inside that vertical plane, if you see these two particular links are like joints are like parallel to each other. So inside that plane, so if I just change the color, so inside that plane, it is like a two-hour manipulator. So a two-hour manipulator can reach like any position in the workspace. Okay. So if I give this position, it can reach over there. If I give this position, it can reach over there. So uh, and this it can do in every plane, right? Because the bottommost is responsible for changing the plane. So you can I think you can, if you imagine this, you will get convinced that 3 degrees of freedom arm where the axes are arranged in this particular fashion can reach any position in its workspace. Now the remaining 3 degrees of freedom, I hope you have understood this. And the remaining 3 degrees of freedom are over here. Okay, so there is one rotation about here. Okay, and then there is, if you see this thing, okay, this is nothing but usually this is like the standard wrist configuration. Okay, and I will try to draw it somewhere here. I'll draw it here. Okay, so the wrist, the front part is like this. There is a motor over here. If you open that arm, it will look like this. There will be a motor over here. Then there will be a pulley, and there will be a belt. Okay, and this belt, there will be some bearing over here, and this belt will rotate this link. Okay, the reason we are not putting a motor directly over here is that we want one, that the motor to be as close to the base. It should not be very far away. Okay, and the second thing is we want to have some gear ratio increase over here through pulley. So there should be a smaller pulley and a bigger pulley over here. So the gear ratio will be more. Okay, and one and two, something like that. Okay, so if you have any doubts, I will try to clarify about gear ratios and all. So there is this particular joint, one joint. Okay, now there is another joint over here which says, if you see, so this is what this black part I drew. Okay, this is the black part I drew. Okay, now before that, here if you see this particular region, there is a motor like this which looks at this particular joint. So there is a shaft of the motor like this. Okay, so this is under this inside this entire casing. Okay, so this can rotate along its axis. Okay, so this rotates like this, and this rotates like this. Okay, and then again there is a motor at the tip that rotates like this. Okay, so these two motors seems like they are facing in the same direction now in this configuration, and this is like pitching. Okay, so this two will rotate like this, and this motor will rotate in this plane, the plane of the screen. Okay, so this entire thing is called a spherical wrist. Okay, so if you have, so this particular thing is called roll, is called pitch and roll. Okay, someone wants to join. Okay. So I hope you understood that. Okay, there is this sequence. So first, after we get the 3 degrees of freedom of the initial motors, we have the entire wrist configuration. Okay. So the wrist where the one of the motor is over here for roll, then pitch, and then roll. Okay. I will try to pull up maybe some video and show you this thing. Okay, then you will understand more. But I think you understood. So there is one pulley over here, and then there are these two motors. Okay, so the wrist, usually people assume that it will be very small at the tip of the end effector, but in this particular configuration, you see that the it starts from here actually. There is a motor over here, then there is a motor over here, and then there is a motor over here. Okay, but these two axes are not always parallel. So let's say if you do the pitch, then this part will look downwards like this. Okay, and let's say if you know rotate this 90-degree, it will look downwards, right? And then you turn this motor. Okay, then it will look towards you because it is spinning about the axis. Okay, so first it was like this. You turn the belt motor, it went down, pitched down, right? And then you turn the roll motor which is at the beginning of the wrist, and it will look upwards towards the end effector will look upwards towards. Okay, and then if you want to rotate, you can rotate about this axis. Okay, that is the last roll axis. So this is the end. So you can reach any configuration, sorry, any orientation using this wrist and any position using the initial three motors which we have seen. So this particular arm can simultaneously and instantaneously move in any direction, right? So this is the definition, right? Move in any direction instantaneously. And so that is why it is the holonomic manipulator. So the answer is yes. It is not because it is 6 degree of freedom. It is because it is 6 degree of freedom arranged in a sensible way. Okay. There can be a stupid way to arrange all the 6 degrees of freedom where all the links are in the same plane. 1 motor, 2 motor, 3 motor, 4 motor, 5 motor, 6 motor. Now this cannot move outside the plane even though it has 6 degrees of freedom. So this is not a holonomic manipulator. Okay, it cannot move in any direction instantaneously. Okay, so this particular is. Okay, so that is the answer for it. Uh, okay, let's see a video of holonomic manipulator. Yeah, so here you can see the first angle, then the first angle is roll, then you get the pitch and the way I drew it, right? So here also I will try to show you some industrial video. Yeah, see here. So this is also one design. So there can be different designs. Okay, for the wrist. So here also you see there are 3 degrees of freedom. Okay. Okay, you can explore later on, but I think I have explained in sufficient detail. So when you try to build your own robotic arm, these decisions you have to make on how to, have the how many degrees of freedom to have. So for a holonomic arm which can move in any direction, you need 6 degrees of freedom, and that makes the robotic arm very costly. But also you make sure that your high duty motors are at the base, near the base, because if they are at the end of the manipulator, there is lot of torque requirement to lift it up, right? So you cannot lift up, you can lift a bucket like this, but cannot lift a bucket with your arm extended, correct? So that is the logic. Okay, let's move on to the next question. uh, Find the values of the joint distance and link length of the Rhino XR3 robot. Okay, so let's follow our rules. So here we are again with the DS parameters. Uh, so what we do is first we label the. I will just erase all of this. We'll do it together. Okay, so first what we do is first we label Z0 axis, right? Z0 axis, X0 and Y0. So this they have done for us. After that, what we do? We label all the joint axes. So Z1, Z2, Z3, and Z4. So yeah, and then what we do? We put the x axis. No, we put the origins, right? So first Z I's along the joint, along joint. After that, what we do? Origins. And how we find the origins? So origins are at the common normal between Z1 and Zi minus 1s. So this will be O1 because the common normal to Z1 and Z0 is at passes through here, right? Again, the common normal Z2 and Z1 intersecting Z2 is here, so O2. Common normal between Z2 and Z3, okay, intersecting Z3 is here, O3 and O4. So we got the origins. Okay, someone joined. Where is the meeting? Okay, so from next, yeah. So we have seen all our O1, O2s and O3s and O4. So what we did was first we did the Z axis, then origins. Any doubt in how we did the origin? So what we did was we followed this rule, right? What is the rule? Locate the origin OI, step 3, where the common normal to Zi and Zi minus 1 intersects Zi, right? And last time we have done enough practice of this. So this time I went fast, but if you have any issue, please tell me. Okay. So this is, so what I did was the common normal to Z1 and Z0 will be what? It will be passing through O1, right? And I wrote it as O1. Okay. So, okay. Then O1 and O2 common normal. Where does it intersects Z2? Here. So O2, O3, O4, same logic. Fine. Then again, we to go to the next rule. We want to figure out how to write x1. Okay, so x1 will be how? X1 will be perpendicular to both z1 and z2. Okay, so it will be along the common normal. Okay, from O1 to towards the along the common normal. From O1 along the common. So this will be x1. Now again, O2 is here. Where is the common normal between Z2 and Z3? This is the common normal, right? So this will be X2. This will be X3. Fine. Okay. And then what? So we have done the Xi's along the common normal. Common normal to Z's. Zi's. Okay. So Zi's and Zi minus 1. So if after that what we do, the simplest step. Okay. So what we do is we locate the yi's by the right hand rule, right? So if you see x is here, z is here, so y should be where? It should be like this. So you feel free to use your right hand and do. And so let me label y with a different color. So y1 will be like this, okay? And similar, this is x2, right? X2 z2, so y2 will be downwards. Okay, x3, y3 will be like this. Okay. Okay, so what we do is the last frame we just copy the axis, okay, and then here we will have a x4 here, and y4 will be where? So we will have y4 in this direction, okay. And now we will fill in the ds table. Okay, so this time no one is asking doubts, so maybe I think it's clear. If you have doubts, please ask. Okay. If someone is joining, so let me admit. Okay, you can just turn on your mic and ask. You don't have to raise your hand, okay? Because I cannot see the meet screen. Suresh, you want to ask something? Your hand is up. Hello, Suresh,
Yes,
can you
sir.
hear me? Yeah.
Yes, now you can hear me, sir.
Yes, yes, I can hear you.
Sir, can you please repeat the axis allocation twice, second time?
Yes,
I
yes,
couldn't
I will do that.
understand axis allocation properly.
Okay, okay, fine, fine. So I will do it from starting. Okay,
From
so
side, uh, from very scratch,
yeah,
from
yeah. So
Z0,
you,
allocating from Z0.
so you were not there last time.
No, sir, no, sir. I was not
Okay,
there.
okay, fine, fine. I will repeat. Okay, so we will repeat
Mm.
from the start. Okay, so let's make it over here. The same manipulator. Okay, so this is the figure given to us, and even they gave us the
Yes.
z0, x0, and y0. Okay, z0, x0, and y0. Okay, so this is the figure given to us. Now, okay, so if you see the rules of allocation of DH parameters, so we went a bit fast. Okay, so I will
Okay,
just
okay.
pull up these rules, okay, that we discussed last time. Okay, so let's have this over here. Okay, oh fine, I will just tell without looking at. Okay, so the thing is, we just there are some rules that we have to follow. Okay, and the first rule is that, okay, locate and label the joint axis z0 and zn minus 1. So when you say joint axis, what does it mean? It means that the how the joint is going to move. So if it is a revolute joint, you move it, put it along the axis of revolute joint. If it is prismatic joint, you put it along the axis of prismatic joint. So if you go to our question, okay, so where the z1 axis will come? So z1 axis will come like this, okay, into the paper, right? You could have put it outward also. That is also fine. Okay, so this is z1. Again, this will be along. Put all the joint axis. Okay, z2, z3, z4. Fine. And this joint was rotating anyway upward like this. Okay, so the z0 axis what they have given is right. Fine.
Okay, why we take Z1 in that direction? Why don't we take that in this X0 direction? Z1.
Because it should be so it is written, what is written, it should be along the joint axis. Z's are
Okay.
always along joint axis, so it is rotating
Okay.
in like this na.
Right. Right. Okay.
That's why
Yes. Yes.
all Z's will be like that. Okay, now
Okay.
after that, the second, this is step 1. Okay, let's look at the second step. Okay, so what is step 2? This thing is coming in front. Okay, here it's visible. So establish the base frame, set the origin anywhere on the z0 axis, and x0 y0 axis are chosen conveniently to form the right hand frame. So for this particular question, we don't have to do that because they have given us. Okay, if you look at this question, where is the question? Yeah. So x0, y0, z0 they have given us, but we could have arbitrarily chosen x0, y0 that is perpendicular to z0. Okay, and we
Okay.
would have located o0 anywhere along this axis, but we will choose to locate it along at the uh, joint. Okay, now the next step is step 3. Locate origins OI where the common normal to Zi and Zi minus 1 intersect Zi. Okay, so for the first time it might sound that I have said a long sentence, but basically it means this. Okay, so it is saying that you have Z1 and Z0. Okay, so Zi and Zi minus 1. So because they are saying I, because we have to do for all i's, all joints. Okay, so for I equal to 1, what is Zi and Zi minus 1? Z1 and Z0. Okay, so for Z0, Z1 and Z0, what is the common normal? What is common normal? The line that is perpendicular to both Z1 and Z0. So what is the common
Z0.
normal? It will be along some this direction, because this is Z0, the green one is Z0, pink one is Z1. So perpendicular will
Yeah.
be along this line.
This line horizontal.
Yeah. And where this common normal intersects Z1, that we should label as O1.
O1. O1.
Okay.
Okay.
So the intersection of common normal and Zi minus 1 and Zi will be O1, OI. So this is O1. And by the same logic, if you see Z1, Z2, the common normal will be along this line, right?
Okay.
And where does this common normal intersect Z2? Here, O2. Similarly, Z2 and Z3, common normal is this line. And where does it intersect Z3? Here, O3.
Okay.
Similarly, O4, right? Okay. So we are done with the step 3, that is labeling of OI. Step 4 is that we have to put our x-axis, xi, along the common normal. Okay, so this was the common normal. So we'll put x1 like this. We could have put it in the opposite direction also, but we choose here.
Okay.
That is your choice. Okay, so here this is like this. Now what is the common normal between Z1 and Z2? Vertical. Okay, and we write it like this. Okay, x2. Now O3 and O2 is there. Okay, and the common normal between Z2 and Z3 is along this line. Okay, so we have to put it perpendicular to the common normal or along the common normal. Along the common normal. So what is this? It will be, you can put in this direction or this direction. So let me check. Okay, so when you get confused, go back and check. So what they have said, establish xi along the common normal between Zi minus 1 and Zi through OI. Okay, so Okay, so common normal between Zi minus 1 and okay Z2 and Z3 through O3. So it will be X3. I can put it forward direction also, not a problem. Similarly, this is the common normal, I can put X4. Okay.
Oh,
Now how do I put Y? Y will be, yi will be, it will be one which will complete the right hand frame. What is right hand frame? If you rotate X to Y, you should get Z. You do a counterclockwise rotation from X to Y, you should get Z. So this particular thing is fine. X to Y, if you rotate, you are getting Z. Okay,
right,
so
right,
this is X1. So Y1 will be where? Downwards.
right.
Okay. Now this is Z. Where is Z2? This is Z2. The pink one is Z2. Black one is X2. So the common normal will be where? Left, right, down. It will be like this, right?
Mm,
So that way you put all the Y2s,
right.
right? And we are done. The only thing is at the end, for the end effector frame, you copy the frame that is just before it. Okay, then you are done. Fine. So now what we should do is we should fill in the DH table. It is not able to erase. Okay, we'll make a new one. Okay, so we have to fill in the DH table. Okay, so this is I, 1, 2, 3, 4. Okay, so we have theta, we have alpha, we have D, and we have A. Okay. Okay, so let's go to the question. And what they have said that, okay, this is the question. And they said that find the values of distance and link length. Okay, but let's find all the DH parameters, not just this. And they have given some values to us. There is 300, 210, 210, and 75. So let's put that. So this was 300. This is 210. Then this is what? 210. And this is 75. Okay. Now, the important thing is what is the definition of theta, alpha, D, and A? And that also we studied last time, and it is given over here. Okay, so that I will pull up.
Sir, just a minute.
Hmm.
सर ये जो स्क्रीनशॉट है ये स्टेप्स के स्क्रीनशॉट दे दोज आर फ्रॉम विच बुक सर
Yeah, that I will tell you the name of the book. Okay, but for now you just focus on the
ओके ओके
question. Okay, yeah. So this is from Vidyasagar and Spong. Spong, robot dynamics and control. Okay, I will just type in the chat also before leaving. Okay, so AI
ओके
is the distance along xi from OI to the intersection of xi and zi minus 1. Okay, so if you see the distance along xi, right, this is the distance. What is the distance along xi, x1? Okay, from O1, from O1, okay, to the intersection of x1 and Z0. So that intersection is also O1 only. So there is no distance, right? So this is 0. Okay, fine.
Right.
Similarly, if you do for the next, you fill in. So what is the this thing? Distance along x2, distance along x2. Okay, what is distance along x2? This will be 210. Okay, so this will be 210. Then we have distance along x3, distance along x3, that will be minus 210. Okay, and distance about y4, that will be minus 75. Okay, and similarly d will be what? Distance along z, so this is 300, and then you will have zeros everywhere that you can check, because along z axis there is no distance, right? Along z axis there are no distances. So d, if you see, it's along z axis. Okay, so since we are in practice, we don't have to read each and everything. Okay, and this is what they have asked us. Okay, but the important thing you should notice, this is not a unique answer. Let's say if you would have put the x3 ulta in opposite direction, you had the choice na, according to the rules, then you would have got plus 210. Okay, so that is why this is not a unique answer, but this is the answer for this particular question. Okay, we'll check our answer. Yeah, so this is okay. So yeah, the answer is downward. Where is the answer? Yeah. So this is the answer. A is 210, 210, 75, and then there is this 300 and 151.5. But we don't have to worry about that this thing. So let me check why it is 151.5. Yeah, because of our this mess, we actually skipped this particular value. We didn't see. Okay, I don't know how to bring that up. Okay, that 151.5 was also there, but now you just have to look along the z-axis or along the x-axis, depending on whether it is d and a, and you can get the answer. Okay, so I think it's fairly simple. And last time also I had shown you where you can get more examples to practice that. Today also I'll put the link, and if you it's about practice. Okay, so let's move on to the next question. Or it was the last question. No. Okay, my slide. Okay, let me just do some kind of. We will get over with this quickly, and then we'll go to the MATLAB animation of robotic arm. Okay. I think most of the questions are done. Yeah, there is this one question that is hiding over here. So choose the false statement. Why it always creates this? I'm sorry for this disturbance, but okay, I'll make a. Okay, so this is the question. So choose the false statement. Are you guys with me? Can you hear me?
Yes, sir.
Anyone? Yeah. Yeah.
Yes,
So
yes,
sorry
yes.
for that mess on the slides, but okay. So choose the false statement. Manipulator tasks are normally formulated in terms of desired position and orientation. Yeah, that is true. Right. So multiple solution exists and unique solution does not exist for inverse kinematics problem. So can anyone tell me what does inverse kinematics mean? So this word came first time. right? So we learned about forward kinematics last time, and we coded it in MATLAB. So inverse kinematics maybe we'll do next tutorial. So what is inverse kinematics? So inverse kinematics means that you have been given the end effector position, the tool position, tool tip position you have been given, and you have to find what are the angles of the individual joints. Okay, so it is a very useful thing, right? So usually the task is defined in terms of the tool position, right? I want to weld over here, and along this line I have to weld. So I know the end effector positions, all the welding on the car, what location I want to weld, I know that. So what I want to know is what angles my robotic arm should make, joint angles, so that the robotic arm will do that. Okay, so that I can give the command to the robotic arm. Okay, so that is the inverse kinematics problem. But the challenge over here is, even for the simplest case, let's say a 2-hour manipulator, you can see that to reach this particular position, how many ways we can reach? How many solutions are there of theta 1 and theta 2? Let's say this is theta 1 and theta 2. So what are the, how many answers are possible if I want to reach this x and y and effector position? Please answer. So one solution is in front of you on the screen. The other solution can be from this side, right? This particular link can rotate all the way like this, right?
Yes.
And the top link can come like this. And this is also a solution. Okay, so there is no unique solution. Okay, so can there be a unique solution, or never there is a unique solution? For a 2-hour manipulator, this is more interesting question. So is it possible to have a unique solution for a particular position of the end effector? So it turns out, obviously, so if let's say this link length is L1 and L2, and you give a coordinate what you want to reach on a circle that is of a radius that is L1 plus L2. The radius is L1 plus L2. What will happen? The manipulator will have to become completely stretched. Okay. So this is something called as singular configuration, and we might learn about it next time in more detail. But you can see that there is only one solution for it. Is it possible that inverse kinematics have 0 solutions? Answer is yes. If the point is outside the workspace, if I want to reach here, the length is only L1 plus L2. It cannot reach here. Anything more than L1 plus L2, it cannot reach. So 0 solutions, 1 solution, and 2 solutions. All 3 are possible. Okay. Can there be infinite solutions? Can there be a end effector position for a 2-hour manipulator with infinite solutions? Who, I want an answer from the audience.
यस सर, मुझे यस लग रहा है.
हाँ, तो कहाँ पर होगा वो? Where
इनफाइनाइट
should the point
सॉल्यूशन हो
be?
सकते हैं, क्योंकि जो L1 और L2 है वो मतलब कोई भी डायरेक्शन में से मूव करके हम पर्टिकुलर रीच पॉइंट पर रीच कर सकते हैं.
Yeah, but I am asking for theta 1, theta 2 angles. Theta 1, theta 2 का कितना combination possible? So let's say if this is a position we want to reach, let's say अंदर है. Okay. To reach here, I can have
Yes.
this theta 1 and theta 2, or from this direction I cannot have more than these two, right? Theta, एक
Yes,
theta 1,
by
theta 2
also
इधर, एक
changing.
तो, so I want to reach here, right? So one direction is here, and another
Yes.
direction is like this. This and
Right.
this, because there are only 2 links. Okay. But there is a point in this entire workspace where infinite solutions are there. On the circumference of the straight link, there is only one solution. Okay.
Yes.
If I point over here, L1 has to be here, L2 has to be here, like that. Only one solution. You cannot go from this
Right.
side or that side. Why? Because it completely stretched. Theta 1, theta 2 का ये angle हो सकता है. Only this angle is possible. Okay. So there is a point, and it is very simple to miss that point. That is the origin itself. If I ask the robotic arm, ये robotic arm ऐसा है. Ask this manipulator tip, that is the end effector, to reach this point 0, 0. It can reach in any infinite ways. You rotate it completely like this. After you rotate
Yes.
it, it look like this. Okay, assuming L1 and L2 are equal. Okay, it will look like this, and this can be at any position. Here, downward, leftward, rightward.
Yes.
Yeah, so these are
Yes.
infinite solutions. Okay, so the question was multiple solution exist and unique solution does not exist for an inverse kinematic problem. Yeah, so the answer is
Sir?
true. Hmm?
Yes, sir. I can go to the 0, 0, not once, but twice, thrice,
Yeah.
a number of times. No, because I can make a full
Yes,
360
yes. So
and
it
come
is
backward.
infinite. Yeah,
Infinite.
infinite solution. So if the end effector position is at the origin and you have equal length links, okay. If your second link is short, you cannot reach that position. Can you imagine that? See, if your first link is big and second link is only this much, you cannot reach the origin. Then infinite positions are not possible. Solutions are not possible. Okay.
Yes, sir.
So yeah. So if you have equal length links, then it can completely overlap like this and can approach from an entire 360 degree, right? And then infinite solutions are possible. If it is on the end effector position is on the circle, okay, of the length L1 plus L2, then only one solution is possible. And if it is inside that circle, then you have two solutions possible. That is multiple solution. And if it is outside the circle, then no solution is possible because our link, it is outside the workspace of our link length are not sufficient to reach there. Okay. So the answer to this question is actually multiple solution exist, true, and unique solution does not exist is wrong. Actually it's wrong, but the question didn't ask us to think so deeply. So unique solutions are possible if the point is on the edge of the workspace. Okay, but here it's asked in general, so I think this is what they give the answer. Okay, so you can tick over here. If they ask inverse kinematics, multiple solutions are there, then yes, that is true. Okay, but unique solutions are also possible if the point is on the surface area of the workspace. Okay, uh, a systematic closed form solution applicable to robots in general is not available. That is true. Okay, so for 2R manipulator, you can derive through geometric relationships a solution to the inverse kinematics problem. We will see it next lecture. But when the robotic arm becomes too much complex, then it is not possible to find that closed form. When you say closed form, it means a formula. You cannot find an analytical or just a formula for it. You have to do some other methods to do that. And inward problems are more difficult than forward problems. Truly, yeah, it is true because there are multiple solutions sometimes possible, and the formula is not available. But forward kinematics is very easy. We have seen all the questions before this. Is just you follow the rules, you find the DH parameters, you find the homogeneous matrix for each link, and you multiply all the homogeneous matrix. You get the final complete homogeneous matrix from the origin to the end effector frame, and that in that homogeneous matrix, the three terms, the fourth column and the first, second, third row, the three terms are the position of the end effector with respect to the base frame. Right? This is what we saw. Okay, and we are done
Sir.
with all the questions today. If you have any doubt, we can take up, or we go to the
Sir.
MATLAB and code.
Sir, just as a thought experiment, suppose there were theta 1, theta 2, and theta 3
Okay.
in three axes, and we had to reach a point in which all the arms are of equal length, and we had to reach a point. How could it possibly be, sir? Would that be infinite solutions or
Yeah.
something
So
else?
so so if in case of three
PW7.
link lengths. In case of three link lengths, you can reach a particular point. Any point you can reach. In a
Uh,
multiple ways you can reach. Okay, but whether you can reach
yes.
in infinite ways or not, you have to think. Okay, any arbitrary point you
Oh,
have to think, because it's not necessary that it's
yes.
possible. But you think reverse. Okay, so I will give you a hint. Suppose the point is comfortably inside the workspace. Okay, it is not at the edge of the workspace. Then you
Uh,
draw a sphere of the third link, of the size of third link, from that point which you have given me, whether you
yes, sir.
can reach it or not. And on that sphere, can you reach using a two-hour manipulator? No, right? Because two-hour manipulator can move only in a plane. Okay,
Oh, okay, okay,
okay.
okay.
But on that sphere there will be a circle corresponding to that plane,
Yes, sir. Yes,
yeah,
sir.
on which you can
Yes.
move, because in that
Oh,
plane you can reach any position using a two-hour manipulator.
yes, sir.
Okay, so
Thank you very much.
if the point is comfortably inside the workspace, you can have infinite solutions. Okay, if you think that
Thank
way.
you.
Yeah,
Thank you very much, sir.
yeah. So okay, so let's any other question. Okay, so I didn't switch back to this particular slide. Okay, but no problem. It's fine. Okay, so let's go to the MATLAB. Okay, so last time we had seen that. Okay, let me pull up the code. The week two. Yeah. Okay, so this thing is optional, but it's good to know that whatever you learn in the course, how to apply. This is not a part of the syllabus at all. Okay, so what we did was, if we have the DS parameters, what do we do with it? What is the application of forward kinematics? And as we discussed, one of the application of forward kinematics, it actually helps us to animate the system. Okay, so how do we do that is, so we have the L1, L2, the link lengths, and we have found the for DS parameters for the two-hour manipulator. Okay, the manipulator whose workspace we were discussing currently, A1, A2, alpha 1, alpha 2, D1, D2, and theta 1 and theta 2. So theta 1, theta 2, we can give the values. These are the joint variables, and for each of the link, there are two links. We found this particular matrix. Okay, A1 and A2, and this matrix we found using the formula that we had discussed in the slide. Okay, today also we saw that formula. Okay, so A1 into A2, if we do, we get the total homogeneous matrix from the end effector to the base. Okay, and if I take the first the if I extract the positions. Okay, here these are the end effector positions I extract. Okay, let me switch to the MATLAB window in the recording. Hmm. Okay. Okay. So I extract the positions, and then we get the end effector position over here, the X position, Y positions. This is the end effector position, and then this is the previous link end. So we need to draw. We need 3 points, right, to draw a two-hour manipulator with, and we run this code and we drew like this. Okay, so this is the two-hour manipulator. If you see here, theta 1 is 30 degree, theta 1 is 30 degree, and theta 2 is the angle between theta 1 and theta 2, and that is minus 90 degree. Why minus sign is there? Because it has rotated clockwise direction. Anti-clockwise direction you can see as plus 90. Okay, so this is what we see, and if we want to, let's say, animate this such that let's say we give certain certain number of certain sequence of angles, and then it should move. Okay, so how we do it, that is, instead of giving one angle, what we do, we give it as, okay, we create theta 1 should be a sequence of angles from, let's say, from 0.002 with a 0.1 step you move to 30 degree. Okay, or let's say 1 degree step you move to 30. Okay, I will show you what this command does is, so the colon operators are there and it will create an array from where numbers are from 0 to 30 with the step of 1. Okay, so if I run this in the command window, okay, like this, so you see that from 0 to 30 I got all the numbers with a step size of 1. If I would have done 2 over here, I would have got with the step size of 2. Fine. So I want from 0 to 30 degree, the first link should move. And similarly, I want 32nd link to move from 0 to 90 degree. Okay. But if you see the number of elements in the first array and the second array are different, right? So if you want the number of elements in the first array and the second array as same, then what you can do is, instead of this particular command, you can use a linspace command. Okay, so there is something called a linspace, and you give the initial value as 0, final value as you want as 90, and the last value is how many numbers you, how many partitions you want. I want 100 partitions. Okay, so more partition, the more smooth your animation will be. So 0 to 90 and 100. So let's make it 30. Okay, the position what where we saw, okay, there we want to reach from a 0 0 position. So and first angle 0 and last angle 0, so the link will be like horizontal. Okay, from horizontal we want our link to look like the way it was looking now, like this. It should look like this. Okay, not like this. So for like this we need a minus 90. Okay, so we want this. So theta 1 theta 2 we have. So what we should do now, we should use a for loop. Okay, so using for loop in MATLAB. So for I is equal to, so if usually we don't remember these commands, right? We just go to Google and we have to just search for loop in MATLAB. You will get the syntax. It's not a very rocket science. Okay, so you just search on Google and get the syntax errors solved. So if we get some error, we'll go to Google. Okay, so for I is equal to 1 to 100, we have 100 values, right? And end. So whenever we use any loops in MATLAB, you have to use end. If you do use if, there should be a one end associated with it. Okay, so for and end we put. Now inside that we will write our code. So what we have to do? We have to apply this transformation, right? We have to apply this transformation, and we have to apply this transformation how many number of times? 100 number of times. Okay, so we can use function for this, or we can just use copy this code inside this. Okay, okay, and now theta 1 theta, these are all arrays, right? These are arrays, so we want to say that the ith element of theta instead of theta. Okay, so in order to do that, I have to put I over here. Everywhere I have to put I. Okay, the better way would have been to use a function, but okay, here we can do that next time when we do it, a more interesting case of inverse kinematics. Okay, because then that will look like a use case, actually something that can be used for a practical application. Okay, so that's I over here. Okay, sorry for putting I in alpha. Alpha is going to have to put I. Okay, only theta's value we have to put I. Alpha is constant. Right? Theta is the joint variable. Okay, it's variable. It varies with time. That's why we call it variable. Okay, so that is fine. Every theta has an I associated with it. If we forget, no problem. It will remind us by giving us an error feedback. Okay, you put an I everywhere. Okay, so okay, any theta 2 remaining? Yeah, this one. Okay, so what it will do is it will calculate new A1, A2 for every theta, right? Because we are doing for 1 to 100. Okay, and then we'll get a, and from A we have to extract our. So this code will pull up. So we'll extract our positions from the homogeneous transformation matrix. That particular column, we'll get our x and y. Okay, so one way is you compute this completely first, and then you animate, or you can animate while compute and animate. That also you can do. Okay, so I plot every time. Okay, so if I plot every time, what will happen is, so let's see what is happening over here. Okay, if I run this, did I get an error? Okay, so what we have to do, we need to have some delay given to the system. Okay, we give for every time you plot, because it should not happen very fast. You do this and we clear this. Okay, I will explain the code. Uh, let's get this running. Okay, so you see here what is happening is it is moving, but we are not able to visualize it properly. Okay, for that we have to set the limits here. The size of the screen must not change. Okay, so you see here it started from a 0 0 position. Is everyone able to see the screen? Hello?
Yes, sir.
Yeah. So the you see that the animation lasted for small time. If you want to last it for more time, let's have 1,000 values. Okay, and here 1,000 values. Okay, and I run this. So it started from 0 0, and then it's moving with a zero point 0.1 degree, 0.1 second delay. It is changing its shape, and it will move to the 30° and 90° position. Okay, so it's too slow. Let's make it fast. So if you want to stop the code in between, you go to the command window and press controls. That way you can stop the code. Okay, so let's make it 300 instead of. Okay, now if I run this, hmm, so you can see the first link theta 1 going to 30°, and the second link with respect to first link rotating minus 90° clockwise. So I mean 90° clockwise or minus 90°. Okay, so any doubts in the animation? Uh, so this is the application of forward kinematics. So even if you, let's say you did a code for inverse kinematics and you found theta 1, theta 2, theta 3, you were given, let's say the you are working on a drawing robot, and that robot has to draw a circle on a wall, and let's say you know the coordinates of the end effector, the wall, the circle under on the wall, and now you applied inverse kinematics and you found the joint angles of the robot. But if you want to, if you are on a real robot, then you just give the joint angles to the real robot and the robot will move in that direction, and you will get the circle on the wall. But if you want to do animation, you don't have the robot, then what you do, using the theta 1, theta 2, theta 3 values that you got from inverse kinematics, now you apply forward kinematics and do this animation. Okay, and so you can see the how the robot is going to behave in animation the way we saw. So that is the application of forward kinematics. So we are done with all the content today. If you have any doubts, please ask, or we can end the session. So any doubts, anyone? So since no one is answering, I will assume there are no doubts. So thank you for coming,
So
and
yes,
we'll. Okay, Anand
thank
wants
you.
to say something.
Thank you very much.
Yeah,
Thank you, sir.
yeah. So I will put up. Okay, I will share the link of the book in the chat. Okay. Uh, it is not a very costly book. But it's not compulsory. There are a lot of good books available. You can check what the course is suggesting. That also you can follow, and the course is also very much good. So this is the link for the book. And if you want additional practice examples on YouTube, I will share that. So there is this Angela. So this is the copy.
Hi, my name is Ben Rat.
Yeah. I'll just copy the link of the video, but you go to the channel, you'll get DS parameters video on this, and there are a lot of practice examples here. And this particular recording will be uploaded to my channel, and my channel link I had shared last time. For those, if suppose you didn't attend this time, then for you, I will just if you just search my name Suraj Borate, you will get the videos. That is also fine. Okay, so this is my channel. Don't need to have the link. Okay, luckily. Okay, fine. So bye everyone. Thanks for attending. We'll meet next Sunday.
Thank you, sir.